Hello, everyone. Thank you for being here this Friday. My name is Will Claridge, and I am a senior studying civil and environmental engineering. And today I'm going to be discussing utilizing algae as a resource to create biofuel. Living in the Madison area and in the Midwest in general, we have all heard of the toxic algae blooms and seen the beach closings and warning signs, which gives algae a bad reputation. The two pictures show algae blooms in Lake Mendota and along Lakeshore Path, a familiar sight I'm sure to a lot of us. Considerable effort is being done on ways to reduce the algae growth in many lakes, but what a lot of people don't know or consider is that algae has the potential to create a better and greener future. To begin the presentation today, I will discuss the need for growing algae. I will be reviewing some of the information in my previous presentations to give a quick overview of using algae as a source for biofuel. I will then go into the two major forms of algae farming as potential solutions, the first of which is an open pond system and the second is an enclosed system. Finally, I will compare the two and then recommend a solution based on my research that I have done. Biofuel use in the United States has been increasing since the 1970s. The U.S. Energy Information Administration predicts the U.S. biofuel production will continue to increase through 2050, primarily driven by economic and policy factors. As increasingly aggressive climate policies seek to limit carbon emissions, biofuels have seen increased interest, also driven by the increase in price of fossil fuels and the goal to reduce the U.S. reliance on foreign oil. A consequence of increasing biofuel production is that it requires farmland and heavy irrigation to grow traditional biocrops, such as corn, soybeans, and other grasses. With many areas of the United States already experiencing water scarcity, an alternative to traditional biofuel crops needs to be considered. So how can we continue to increase biofuel production without severely impacting land or water use for food crops? The answer is algae. In Wisconsin, there are currently 3 biofuel refineries, with the nearest to Madison being in Clinton, Wisconsin, which is about 50 miles south of Madison, and it is shown in the red circle in the picture to the right. This refinery has a capacity of 10 million gallons per year and primarily relies on soybean oil for feedstock. What I want to propose is to build a supplementary algae farm near to the refinery to provide more acreage for agricultural crops. As discussed in my previous presentation, algae is a very good crop to use to produce bio-oils, as it has a very high lipid or oil content and grows rapidly compared to other bio crops. The table shown, taken from ExxonMobil's website, you can see that the oil yield in gallons per acre compared to other traditional crops used for biofuel. I would like to specifically point out that the yield of soybean oils of 48 gallons per acre compared to that of algae, which is 6,000 to 15,000 gallons per acre. Another benefit of algae is that it does not directly compete for land or water use, unlike other biofuel crops, which require land suitable for growing food. The first technique for growing algae that I would like to discuss is an open pond system. This technique for growing algae involves large vats of water that are exposed to the surface. The 3 most common systems are the raceway pond and circular pond, which both circulate the water to mix nutrients, and the third is an unstirred pond, which is just a large pool of water for the algae to grow in. Our raceway pond setup is shown to the right. The main benefits of open systems is that they are much cheaper than closed systems and are capable of producing large volumes of algae. Geomembrane Systems Inc., a provider for algae farms, estimates that the initial costs of an open pond systems are about 1/10 the cost of an enclosed system, which I will discuss later. Additionally, they are easy to scale up as long as there are available land and water. Open pond systems rely on sunlight to grow algae, so no complex lighting is required, and electricity costs are generally low. These systems are also very easy to maintain, as the algae is easily accessible and is not super complex for a system. One of the drawbacks to an open system is that a lot of water is lost due to evaporation. This means that a lot of water is required to run these farms, and this can be an issue in areas of water scarcity. This is further complicated due to the open system's dependence on weather and climate, as the areas with the most sunshine and warm temperatures, such as the American Southwest, typically also have limited water supplies. Open ponds are not suitable for northern climates, as algae cannot grow during the winter. It is possible to build a greenhouse of sorts surrounding the ponds to maintain temperature, but this can get very expensive as the greenhouses need to be very large. Another concern with open ponds is the risk of contamination from bacteria and other algae species that compete for the nutrients in the algae broth. This would lower the quality of extracted oils. The other common technique for growing algae is a closed system or bioreactor. Closed systems have the algae growing in glass or plastic containers and pump nutrients, water, and carbon dioxide through the system, which circulates as the algae grows. The most common type of a closed system involves either thin plates or tubes oriented to maximize light exposure and circulation. The main benefit of a closed system is that all input and conditions are closely controlled. By controlling the nutrient levels, temperature, pH, and other conditions, we are able to grow very high quality algae and produce it in reliable amounts. Closed systems are capable of growing very specific types of algae that open systems cannot, such as food grade algae, which can be used for animal feed. Closed systems typically have a higher yield per volume of water, as it is grown under ideal conditions, and many systems use artificial lighting to grow 24/7. Also, since the algae is contained and not exposed to the air, it can only become contaminated when first filling the system, so the risk of contamination is very low. The main downside of a closed system is the much higher upfront costs. There are much more specialized pieces of equipment that are very expensive to produce, as well as the building that they need to be stored in. Enclosed systems are also much higher maintenance because of all the pieces of equipment that are required to make the system run. Because of the complexity of a closed system, higher knowledge and specialization is required to run these farms when compared to open systems. Finally, the most challenging thing of an enclosed system is the difficulty in scaling the system up. Open systems can expand as long as there is enough land and water to supply them, but closed systems are limited by their ability to pump water through the entire system and storage costs. To decide on a system that would be best suited to supply the Clinton biorefinery in Wisconsin, I used a decision matrix. This matrix consists of 7 criteria, with the most important being weighted highest at 7 and the least important being weighted as 1. I then assign a value based on my research, with the best being 10 and the worst being 1. For example, a high water requirement is less favorable for an algae farm, so I assign the open pond system a lower value than an enclosed since it requires more water. After summing the weighted values, I found that the enclosed bioreactor was the most suitable for this project. The main reason for the enclosed system being the best is due to it being a much better suited system for the climate of Wisconsin, as an open water system would not be able to operate in the winter. The enclosed system is also much more efficient when looking at the yield per acre. According to research done from the National Renewable Laboratory, open algae systems can yield 10,000 gallons per acre per year, while a closed system can yield 50,000 gallons per acre per year. This difference in yield is largely due to the enclosed system's ability to strictly control the growing process of the algae. To help supply the growing demand for biofuel without directly competing with agricultural crops and land, I believe it would be best to build an algae farm near to the Clinton biorefinery located south of Madison. An enclosed algae farm would work best mainly due to the limitations imposed by Wisconsin's climate and geography. The ability to closely control the growing conditions of the algae also yields the greatest amount of algae per acre and would provide a very reliable source to turn into biofuel. If we were to build a 5-acre enclosed algae farm to supplement the biorefinery, it would save 5,200 acres of soybean cropland. This is an area equal to a little over half of the size of Lake Mendota. The next steps of this project would be to conduct an extensive cost analysis. I would want to investigate offsetting the cost of this algae farm by utilizing that 5,200 acres to grow other crops, as well as the profits from the oil this algae will produce. Thank you for listening to my talk today, and I hope that you have a new appreciation for algae and believe that it is capable of more than just closing our beaches and lakes.